Okay, I think we can start. So in the last video, we learned about inference for latent variable energy-based models. We'll just quickly go through that so that we know about the context. Yeah, so this is basically a toy example. Yeah, that makes it a bit disappointing. Like most of the thing is just deals with toy examples. I wish he had shown more real world example, but that's what we have. um yeah, so the specific thing that we have to note in this problem is it's he refers to it as multimodal output. I don't know if it's the right terminology. So essentially for each x you have many outputs, right? So if you look at this diagram, you have an x and the output is a 2D vector, a 2D y vector. So you have something that looks like a horn, and for each x you have y1 and y2. um, and if you look at a cross section for a particular x, you have something that looks like this. And yeah, so that's why he calls it multimodal output. And each of these points is like the manifestation of a particular value of the latent variable. So by varying the latent variable, you get something that looks like an ellipse. So for a particular x, as you vary the latent variable, you get this ellipse like structure. And so in this particular case, everything is known to us. The whole data generation process is known to us. It's basically this, right? Y is a 2D vector, x is your input, and this theta is the latent variable. And theta is obviously the angle in this case, the ellipse thing. It varies from 0 to 2 pi. So this is the data generation process, and epsilon is just a small error that's sourced from a normal distribution. um, and then yeah, this is like the model manifold. So you train your, so you have a model which gives a model manifold, and your target is to somehow make this model manifold match with the actual y points. Yeah, that is in the training process. We'll be looking at that. um, and yeah, this is the energy function. Energy function of any point y is basically its distance from the model manifold, right? And so this is what it looks like. This is the Euclidean distance basically. um, y1 minus, this is the point on the manifold, and any point on the manifold is just a function of z, right? Because we are taking a cross section at a particular x, so that's why there is no x in here. This is just a cross section at a particular x, and any point on the manifold is just a function of the latent variable now. And yeah, so it's the Euclidean distance. And yeah, we have seen all of this in the previous lecture. So free energy, uh, so this is this is what is called zero temperature free energy. um, it is the minimum of EYZ, the minimum value of EYZ. So essentially what it means is, uh, for that particular point, you consider only the point on the manifold that is closest to it, and then you find the energy. So that is called energy, which is the Euclidean distance from that point to this point. Um, so that is called zero temperature free energy. Okay, I think we have seen all of this. So yeah, this is just a graph of what the free energy looks like. So considering that your manifold is somewhere here, at that point the free energy uh, is zero, and as you move away from it, it increases, and even inside that manifold in the interior it's a bit higher as well, and outside as you go it's much higher. And yeah, so uh, the shape actually looks something like this, like a bathtub shape with a particular with a like an upward dent in the middle. um yeah, so this is actually the uh, contour diagram of this. And yeah, so since you have this region of high free energy in the middle region, that's what gives this dent in the middle. Yeah, so if you take a cross section of this, it looks like this. And yeah, so this is actually uh, yeah, this happens when you take zero temperature free energy. You have this sharp upward spike in the middle. And so yeah, so what happens with zero temperature free energy is you are actually overfitting. uh, so we'll see about that as well. And how the way you avoid that is by increasing the so-called temperature. And so in free energy, as we already saw, it's just the Euclidean distance to the nearest point from the model manifold. So if you take a particular y, we just take the nearest point from the manifold and find the distance. um, yeah, so this is z, I don't know how you call this, z hat. It is the z for which the energy is minimum. And the way you relax this is by using this f beta of y. um, and so this borrows a lot of things from physics basically. So beta is, I mean, there are equivalencies with physics. Beta is called the inverse temperature in physics, and this is basically Boltzmann constant times temperature, and the whole thing raised to -1. So that's why this whole thing is called inverse temperature. So if you look at this, so what happens is, if you drop the temperature down to 0 Kelvin, or if you approach that value, beta becomes infinity, right? Since you are dividing by something whose limit is approaching 0, and that is equivalent to this thing. Yeah, so this equation just becomes this zero temperature limit free energy. And yeah, and so for any other, so when temperature is 0, it is called this zero temperature free energy, where you just consider the nearest point in the manifold to that particular point. And this integral can be discretized. So integral is just a summation, right? And you can discretize that uh, while going through all the z points, all the values of the latent variable. And Yeah, so maybe this diagram will help it to understand it a little bit better. So this ellipse that you see in the middle is the model manifold, and suppose you are considering a particular point here. um, so in the zero temperature free energy, you would only consider one point that is nearest to it, and the distance would become the free energy. But when you increase the temperature a little bit, you consider few more points in that vicinity. And how do you, and the way to understand that is basically, here uh, you have this expression which is e raised to minus beta energy of y comma z, right? And this z is the latent variable that you're varying. So as you vary z, you are actually looking at all of these points in the manifold. The manifold is just a parameter of z, right? And so the thing to see here is, if your uh, if your current y is close to that point, then your, okay, let's assume that your current point is far away from this point. So what you're doing there is e raised to a large negative number. So the whole value becomes negligible, right? When you do something e raised to a large negative number, the whole thing becomes negligible. So that's how you are actually ignoring the points that are far away. And then for points that are close by, you have e raised to a small negative number. So it's not negligible anymore. You get an actual value, uh, a considerable value there. And yeah, so that's how the free energy at any particular location, uh, it considers uh, a few points that are in the manifold nearest to that particular point. In a way, it's, yeah, you can consider this like a weighted average of the energies uh, in the manifold closest to it. And and if beta is 0, um, when you do the calculation of the limits, what you end up with is um, average of all the energies. So I think in that case, the whole concept of latent variable just breaks down. So the free energy at any point is just the average of uh, all the energies. So yeah, there, I mean, this is basically useless because it just does not consider the latent variables in that case. And yeah, in that case, I think what he said was it becomes equivalent to doing simple MSc and all. So yeah, then mm, okay, yeah, please ask if there are anything that's, if there's anything that confusing. And yeah, this picture just signifies the same thing. If you're trying to calculate the free energy at this place, um, it considers the energy at this. So this graph basically indicates that, so at this points the energy is higher, and all the other points have, sorry, the energy is lower, and here it's, sorry, here it's higher and here it's lower. Mm, yeah, and this just shows that as you increase, or is it decrease? So when beta is infinity, that is zero temperature free energy, you have this kink or this upward spike that we talked about. And as you increase the temperature, that king just goes away. And then he talks about the different, just a nomenclature difference. So what is actually softmax and what is referred to as softmax in PyTorch. um, so this thing that we talked about, the formula that we talked about, is actually the softmax of the energies. And what is referred to as softmax in PyTorch is actually soft argmax. um, and the actual softmax is, the way you do it in PyTorch is torch.log sum x. I did not understand it completely, but so I think in Torch softmax, in torch.softmax, as it is done in PyTorch, you get a probability of, you get a probability distribution, right? And I guess in softmax, the actual softmax, you just get a single value, which is like the weighted sum, the weighted average. And then we move on to training, like how do you actually get that model manifold. So for training, obviously the main thing that you need is a loss function, right? And a functional is just a function of a function. That's what the meaning of functional is. And so you have this total loss function, uh, and it takes in the energy function that you have and the list of labels, that is the list of, that is the all the y values, to calculate the total loss function. And it is basically an average of all the per sample loss functionals that you have. So you just go through all the training samples and then you calculate the loss functionals for all the training samples. And there are a bunch of loss functions that you can implement. So this is the simple energy loss functional. um, so this is basically, so what happens in this particular thing is, you take an actual data point and the energy at that particular point is considered as the loss. The idea is, I mean, we have seen all of this before. The idea is you just want to suppress the energy of all the training data points, right? This makes sense, right? Energy at all the training data points should be as low as possible. So you can just take that as your loss. And then you have the hinge loss. So hinge loss is the contrastive method, where you have one point which is the actual data point, which you want to, where you want to suppress the energy, and then you have a contrastive point which is not part of your data points, and then you want to increase the energy at that location. And this is what the hinge loss looks like. So the aim is basically, you have a margin m, and there should at least be a difference of m between the energies at your actual data point and a contrastive point which is not part of your data set. I hope this made sense. So this is just trying to maintain a margin between the energies. And yeah, I think generally hinge is better than the simple energy loss functional, because there is a way of breaking this. So you can just set the energy at all locations to be zero, whether it's on the training set, I mean, whether it's on part of the data points or outside of the data points. So this breaks down in that case. Whereas in hinge, you can't do that, right? Since you are enforcing a margin.
The
And
first one represents the manifold as defined by the label data. So basically, it's like, it's just a single line, right, on the manifold or on the energy landscape. So it's like one of these inequalities, right, where everywhere is very high except for this line, right? So there is no way to, you know, anything off the line, it has, infinitely high energy, and anything on the line has zero energy. Hence the, the downward thing on the top of y.
mhm, yeah,
And whereas with the hinge, not only is it for contrastive loss, it's also like a margin loss. You are essentially saying that your prediction and your label must, or any two points on this energy must, if one is positive and one is negative, then they must be separated by some margin. So that gives you a little bit of room. I think, if your data point is not exactly on the manifold, you still can, classify it. Basically, you can say, okay, here I know this, what this is, right? So that's what I got out of it. Sorry, yeah.
yeah, that makes sense. And then you have log loss, which is similar to hinge loss, but it's more smoother. It's not binary as in the case of hinge. So in hinge, um, if it is slightly less than m, then there is no loss. The loss is zero, right? And
Right.
that does not happen in log loss. Okay. Um, okay. I think they're considering this loss for now, and um, yeah. So in this case, they're just showing how the model manifold gets trained. So this is what initially the model manifold looks like. So first of all of these are just like they are like abstractions like of understanding what happens when you train. Um, so what is actually the manifold? The manifold is um so suppose you have the untrained model, right? And you give it a particular x, and it will generate a bunch of y's for that x, right? By, I mean, obviously you have to vary the latent variable as well, and then the shape that those bunch of y's make, that is what the manifold is. So manifold is the lower dimensional surface on which all your points lie. um, and now as you can see, for the untrained model, the manifold lies far away from the actual y's that you have here. And what happens when you train your the target that you want to achieve when you train is the manifold must exactly match with the actual y's, right? And yeah, so that's what we see happening here. And the way you do it is, um, you take a particular y, okay, and then you apply the loss that we just saw. So here the loss that we saw is simply the energy, the free energy at that y, right? So what is the free energy at this particular y? So here the free energy considered is zero temperature loss. We have already seen that, right? So for this particular y, you take the nearest point on the manifold, which is this, and what you're actually doing there is you are suppressing that energy. Now you're trying to make that energy zero, and what happens as a consequence of that is uh, this manifold point gets attracted to this point. I mean, that's how Alfredo explains it. But what happens actually is your model gets trained, right? The parameters of your model gets trained, and as your model gets trained, the manifold approaches the actual y value. As your model gets trained, this particular manifold expands and expands, and it uh, correctly aligns itself with the actual data points. Yeah. Um, yeah. So in zero temperature loss, as I've said, there is a corresponding single point on the manifold which is closest, and you take that free energy and you suppress that, and in that process this happens, the manifold expands, and this is what happens. And in zero temperature loss or zero temperature free energy thing, as I've said before, it overfits, so each point looks at the closest point and it attracts that, and that is uh, just a recipe for overfitting. um, and as you increase the temperature, um, we can avoid overfitting, so multiple points on the manifold uh, kind of get attracted to this single point, and that's how the manifold changes. Since you're just taking the average of the energies, right? And in this particular case, overfitting is less likely. I mean, it's much harder to overfit. But since this is a toy example, I mean, you don't see any. It's the same thing. You don't see any difference. Um, yeah.
And that's something I think like interesting to linger on a bit. So here we cannot overfit because we encode prior knowledge of the actual data manifold into our function. So the data, our manifold is defined by this function mentioned above, which is like it kind of it is aware that we are fitting an ellipse here, right? And
Yeah.
because of that, actually, for this particular task, it's now to have two data points to fit it perfectly, right?
Yeah.
And that's why we can kind of use that simplest loss function there. We do not care about like pushing up the data, the points outside of data manifold, because our energy function is designed in a way that it can output low energy only on the ellipse. And since we are like fitting ellipse to this data which is generated by ellipse, we have a perfect kind of solution. We don't need a lot of data. But if we have a more powerful energy function which can model like a wider variety of possible manifolds, we would encounter all kinds of problems with overfitting, right? And so what is interesting, if you remember when we were talking about like unsupervised learning for in the vision domain, we were discussing a paper called BioL, and there they had like like a deep neural network, which is very expressive function, right? So it can basically express any kind of, or a lot, like a wide variety of possible functions. And still, and they did not use the contrastive loss. And still they didn't kind of didn't got this degenerate solution when you can basically your energy function can output 0 everywhere when you don't have this as you mentioned this data points outside of manifold and you do not do any contrasting. So but in their case they did not use contrastive loss but still converged to a good solution. So like it turns out and at least it's not evident to me how the how the possible functions our network can output are constrained in that case, but still so still it does not the solution is not like degenerate into some constant or whatever. And basically probably like the reason why it happens is in the training procedure they follow. So what I'm trying to say is that probably there are like other ways to generalize your training or like regularize your training to avoid overfitting, other than encoding prior knowledge or doing this contrastive training. So that's interesting. And if anyone knows more about it, I would love to hear.
I think one of the things that, so as you mentioned, right? So initially we basically, assume this in the first diagram here. You basically assume an ellipse that you think is right. It's kind of like, here is my proposed distribution. This is what I think Z looks like. I think the similar thing we do is when we put in, initialize the weights with uniform or normal or something, right? I think that's also kind of similar to this idea, except for a much more generalized domain, that you are encoding some amount of prior knowledge. You're saying, okay, I think, the weights are going to be normal. And then, you let the, weights kind of vary around that, right? Because over the training procedure. And yeah, so that's.
So you think that initialization point can basically determine whether the function will converge to a good solution or to a degenerate solution, right?
Yes, yeah.
Yeah, that's interesting. And yeah, I think there were some results showing that kind of not only the final point, but also the learning path matters. Like when you try to understand what's going on in a neural network.
Arto, what was the paper you mentioned about the unsupervised image training?
Bootstrap your own latent. Okay. It's called by OL.
Okay, thanks. Okay.
Yeah, I think there were other papers which did not use contrastive loss as well. The one by Facebook, probably one of the latest, by this guy Mishra, who gave a guest lecture in this course about unsupervised training. I think it also didn't use a contrastive loss as well.
Okay. I don't know if there's anything else to discuss here.
There is also a concept of temperature in learning rate schedules. When you do exponential schedules, you kind of anneal over time, right? So initially it's a high temperature, and then as you get closer to the end, it's lower temperature. But I don't think they are related here, that temperature and this temperature.
Yeah, there are a lot of inspirations from physics and metallurgy and stuff. Yeah. Okay. Yeah, it's the same diagram again. I don't know if there's anything of note here.
To some extent, this looks like regularization, right? Because you're, essentially, degrading solutions, right? So at at y2 equals 0.5, for instance, your, the zero energy, the red one, the zero energy solution, that's actually better, right? The free energy is lower compared to the blue one where beta equals 0.1. But the good thing is that the surface is smooth, right? So that you can actually afford to make mistakes and not be hurt, right? Yeah. So
Yeah, on the other hand, the blue and probably the green one are like too smooth, right? Because actually we don't have like our data manifold does not include this central region,
yes.
and we want energy to be high there. But this function basically are too smooth to show to like incorporate that into a function, energy function.
Actually, I had a more like I had a doubt on the inference side of things. So suppose you have a trained model, right? So once you train your model, you have a manifold that looks like this, right? And then you're trying to do inference now. So for a particular x, this is what the manifold looks like. And then, so you give it an x, and then you feed some kind of latent variable. So where does the inference part actually come in? So when you give it an x and you give it a latent variable, you automatically get some point, right? So
You get
what
a
is
set of
actually the
points, I think, right?
okay?
So
You get a set of points, and you can. How do you choose one among those?
so basically, I think based on your position, so you get, so again, this is like the distribution, right? So, you're saying that here is my black box, which takes in X and gives me a prediction Y. And I think that the distribution it uses, or the weights that it uses, looks like this, right? What you're seeing in this image, right? So here you just have two inputs. The weight vector is just of size 2 for each input, y1 and y2, he's saying here. And the output y is a function of y1 and y2. Or, okay, the output y is a function of z, which is a function of y1 and y2, right? The z being the latent variable. Now, based on the choice of your latent variable, your y1 and y2 will differ, and hence y will also differ. So that's where I think for a trained model, I think you have to do, I think that's where Arto's point was there, right? Remember, you asked about doing gradient descent on top of a trained model, right? So maybe that's where this comes in. So you basically, look around this, in your trained model, you look for your Z distribution, you try to figure out your Z distribution, and you're saying that, okay, based on this input X, I have this distribution Z. Now I want to find a good point on Z, which will give me a good X value, right? And so the
A good what value?
sorry, a good Y value prediction, Y hat value, right? And your the manifold that you have here will kind of guide you into. So if you choose any of the points in the dark elliptical area in diagram 2, right? Not necessarily on the manifold, but anywhere on that, you are likely to get a good prediction for your X.
Right.
Right. So I think that's where the gradient descent on for trained models, or gradient descent for inference, that's where it comes in.
And
I think, yeah,
it
sorry.
looks like this can be different for like actual inference is for different latent variable models. I think most of the time we are trying to avoid the this minimization, like or how it's called, explicit minimization of the energy function, right? For example, if you take those lectures when we were discussing autoencoders, like we are trying to train an encoder, and sometimes it's called an inference model, to output basically to output given x, output a reasonable z, right? So the hidden variable or latent variable, and that is one way to avoid this minimization. And basically, after in autoencoders, once we have this, we train it end to end, and then we use encoder to output a hidden variable given x, and then we use hidden variable to output our prediction, which in case of autoencoder is our x again, but should be our x again. But you can imagine that it can be something else if you train your decoder in another way. So that's how in that case it would be formulated in a way that we don't really have this minimization during inference.
So just going back quickly to the inference thing. So here, like one thing that he mentioned is you can think of this as I forgot the term. Like if you are having some kind of distorted image and you want to rectify or I don't know, clean that image or whatever. So you have your y, which is the distorted image, and then you can just rectify it by looking at the nearest point on the manifold, and yeah, that would give you a cleaned up image. I think he mentioned this during the inference part. That I understood really well. But yeah, but if you have an X, I feel like all of these points are valid. All of them have low energies, right? So all of them are all valid values of Y. Um, yeah. Like suppose just thinking of it in terms of a real example, like suppose you're trying to generate a face. Um, the face can have a multitude of expressions, right? It can show a happy face or sad or something like that. All of them are valid outputs. You can't say that one is wrong or something, right? So you just have to parameterize it with one latent variable and get an output instead of just averaging out everything.
Right, exactly.
Yeah.
Well, probably that's like this ranking models, Clip, for example, are another way to avoid this kind of minimization. You know, when the OpenAI about this OpenAI DALI work, so they used one network to generate a bunch of images given a text prompt, right? And then they used Clip to rank the generated outputs, and so in that way selecting the most like the best images, right? So basically we have an energy function which is imperfect, and we can sample a bunch of outputs, and then we can use another like approximate model to rank those outputs. And yeah, so I think that is somehow related to this, right?
Yep, looks, yeah, it was very, yeah.
Yeah, I still need to understand a lot about how latent variables are accounted for in actual models. That would be interesting to study.
Yeah, so I think another thing is that you can regularize or apply some constraints on latent variables in a way that you force those latent variables to encode particular features. And there is a bunch of this works related to generative models where in different ways people like manage to learn disentangled latent representations in such way they, for example, can generate faces with different emotions, right? But for that to work, you need to aim to that during the training. So you need to apply some constraints or regularization or something to force your latent variables to encode particular information about the output, or like, yeah.
Gautam, to your point, at least I think it's the third lecture in what we are going through in unsupervised learning, the latent variable models. That whole lecture that we are currently going through, last week we started, and this Sunday we'll go through from the Berkeley course, goes into a lot of detail, but not with the energy concept in mind. So I'm still trying to understand how it works, but the math behind it is very similar in a probabilistic sense, and it gets into a lot of the math, and the math basically provides you the intuition for what is going on.
Okay, the latent variable models courses, right? Or the lectures?
Yep.
Yes.
Yep.
Okay.
Yep.
Okay, thank you.
And this Sunday, tomorrow, I have to go through a lot of the math behind. But it's totally in a likelihood-oriented explanation, not the energy-oriented. But at the end of the day, the intuitions are the same.
Okay, thank you.
Yeah, anyway, like this energy-based models concept, it's more like a framework to think about the models rather than something very like precise, right? So like there are a bunch of works relating any like different training objectives to energy-based model framework, right?
Yeah. Whenever, at least so far, the simple heuristic is whenever energy is low, probability or likelihood is high, and if you flip it, then everything is to a first order equivalent.
Okay. And he was mentioning in the lecture that what we did till now is unsupervised. I don't know why he called it unsupervised, because we are using the y values. So I'm not sure why he used that term. And
Well,
we were
why?
not using x, but x
Yeah.
is, that is x, right?
No, you're using y, two y's in the contrastive learning thing, right? Where you go, I think one slide up, where you have the max margin. Okay, one more slide where you actually have this. Yeah, there, this one, L hinge, right? So you're basically saying, okay, here is y under arrow, right? That is your free energy, and here is y hat, right? And that is your prediction. So one is label, one is prediction, but you could also think of these as being two y's, and you say, okay, here is, find me all the y's that are closed, and therefore that way you'll be able to create a manifold, right? Some space where your things that are closed in that space. Again, going back to the word to vec kind of the side effect of the training, right? You come up with a set of weights which are embeddings, and in this new space, y's that are close together are similar. So therefore, unsupervised. Right. So
Okay. Yeah, that makes sense. And then he calls this part self-supervised learning. So here we are just looking at x as well. So all of this time we were just looking at a particular x and like matching the fitting the manifold for that x. So now looking at the whole thing. So an untrained model manifold would look something like this maybe, and so you have your x and it goes into the predictor, and then you have the latent variables which is 1D, right? It is just a you are just sampling it from 0 to 2 pi. And so the predictor output, and along with the z you get y tilde, which is an ellipse, of course. This is what I mean, this particular this is what forces it to be an ellipse, since you are just varying between angles from 0 to 2 pi. And then you have the actual y values. Yeah, I hope this made sense. And then the energy function. The energy function is basically the same. So as we have told, as I've mentioned before, energy function is the distance from the data point to the manifold, right? The Euclidean distance. And this is the point on the manifold. So this predictor is a neural network, a standard neural network. It has 8 layers, 8 nodes in first layer, 8 nodes second layer, and then 2. So this 2 is the y. As we have seen, y is a 2D vector. So you have an x which goes through a neural net and gives you a 2D vector, and z is the latent variable which ultimately gives us that ellipse. As we vary z from 0 to 2 pi, we get that ellipse for each x. So z is cosine of z sine of z transpose. So this neural net output multiplied by this thing gives you 1 point on that ellipse. And yeah, energy function is the Euclidean distance. And then as we have said before, the way to train it is suppressing the energy at the data points. Yeah, everything else is same as what we have discussed before.
So essentially you're controlling the G1 and G2 values, right? Or the function G1 and G2, which in turn is basically the value of Z here, to get Y tilde and Y as close as possible, right? Or minimize the energy basically.
In a probabilistic sense, this is where it's equivalent to maximizing the likelihood of X that you see given the distribution.
Yep, absolutely. Yeah.
Can you just repeat that, Srinivas?
Yeah, in a energy sense, it's lowering the energies of the points on the manifold, exactly equivalent to increasing the likelihoods, log likelihoods, right? So that's why it's a max likelihood thing when you do it in a probabilistic sense.
Okay. Yeah.
So given the distribution, you're assuming you maximize the observed x's, So what is the distribution? It gives you the max probability of or max likelihood of what you're observing, which are the points that exist that you're observing.
Got it. Okay.
And so in a practical sense, we are training this neural net we had there, like with two hidden layers, right? We train it to predict the parameterization of ellipse given x, right? So we say if x is 1, output me the coefficients for sine and cosine here. So that's our function g, right? Which are the best given the data, right? So the objective is very simple, but we do it, so it's kind of simple. It can be viewed as a very simple problem, right? So we are just fitting two coefficients given one input, but we do it over the not like for one value, but for the whole ellipse, which is parameterized by this z, right? So z is from 0 to pi, right? So it's a range of values, and yeah, that's kind of simple problem all in all, right?
Yeah, it also does one more thing. I think the setup, which is equivalent to it, kind of puts x's which are close to each other also close in the manifold space, and kind of pushes the x's which are not close to each other also shouldn't be close in the z space. And that's something in an energy context. I mean, it's obvious in a contrastive kind of thing, but I'm struggling to get that from this. So maybe I haven't yet listened to this lecture, so I have to go. That's something I'm interested how that ends up happening.
Just to clarify one thing, the only thing that's trained is this neural net, right? There's no other training that's happening. The only thing we're training is the y1 and y2, because that decides the size of the ellipse. You can think of it like the I think it's called major axis, minor axis of the ellipse. That is decided by this neural net. The z is just a latent variable, right? It's just randomly picked from 0 to 2 pi, not randomly, 0 to 2 pi with intervals of pi by 24. That is not the trained part. The thing you're training is this f1 of x, where the size of the ellipse gets decided. The points on the ellipse are just as you vary the latent
the shape
variable.
of the ellipse get decided by the value of z.
How? That's no, z is just giving you points on the ellipse. The shape of z is just giving you different
that's
points
where
on
to
the
me, again, as we, because I've been preparing to talk about the autoencoding thing in tomorrow's lecture, I can kind of, in the keeping that in framework, mentally I can figure out that, see, if you show the equations, there is a g of z there, right? So while you train f1 of x and f2 of x, the g1 of z and g2 of z do have an influence on the decoder and the y and the eventual ellipse you get out. Right. So as you vary, it's my understanding, and that's why I'm struggling to understand that part in an energy explanation. I can explain tomorrow how it works in a probabilistic sense. There is a dependency eventually of the ellipse on the z's too. And right? As it's shown here, because there is a G1Z, G2Z.
Yeah, so the
But how that
energy depends on Z, but the ellipse is not. So like the particular point on this I don't know how the shape is called, but you know, this weird horn. Particular point is determined by combination of x, and this x basically is mapped by a neural network to two parameters which determine an ellipse. So ellipse is not the shape of ellipse, as Gautam said, is completely determined by two parameters, which are outputted by our neural network
X,
and
right,
depend
yeah.
on x, right? So we train a neural network to output basically a shape of an ellipse given an x. That's all it does, and the and z allow like taking particular z from that range of z gives us a one point on that ellipse which is parameterized by x, right? And
Yeah.
if you take the whole range of z, which is from 0 to 2 pi, we will get a full ellipse as we've seen before. So in the previous case, we didn't have x. So we were just fitting two coefficients for sine and cosine right there. And now we are fitting kind of not two coefficients, but a range of coefficients which depends on x, right? And z as before, it just like once evaluated in particular for particular value of z, we will get a particular point on that ellipse.
Yeah, and you cannot learn z, right? You can never learn z. You can never learn a latent variable. You can choose the best latent variable for a given x when you're doing inference, but yeah, during training, I don't think you can. I mean, that's exactly what latent variable is, right? You can't learn it when you're training. It's just random at the point of generation or whatever.
Yeah, but when we select, so we don't learn it, but when we select a particular z, so basically this training over a range of these allows us to like output different possible points on the ellipse for a given x. If we wouldn't have this latent variable, we couldn't learn the horned shape, because in that case we would just learn an average over all data points, which is
Right.
just like lies in the center of this horn, right?
Exactly.
But since we have this z, it allows us to learn a shape, because each particular z value evaluates to a concrete point on the ellipse.
Yeah, makes sense. Okay, I think that at least cleared some things up. Okay. And yeah, once you train the manifold, you get the horn shape of the original data. And yeah, just a couple more things. So here, as it's a toy problem, we kind of knew that the shape is an ellipse. I mean, it goes in circles, right? We kind of knew that, but in an actual problem, we don't know that latent variable would be like that. So here, since we knew that, we just took the latent variables with that knowledge, with that knowledge of the data generating process. So in reality, that is something which has to be learned. I don't exactly understand this equation, but yeah, that's what it says. In reality, we have to learn the shape of z, and so we have a new function g which takes in both the actual predictor neural network and value of latent variable z as well. Yeah, so this is when you move out of this toy problem example, and then here z is a 1D variable, and we don't know that as well. In reality, z could be multidimensional. So here the difference is you consider z uh, as a vector, as opposed to a 1D, as opposed to a scalar value. Yeah, so this is the third type of energy function, where z is a vector and you will have to learn the shape that you get by varying z. Yeah, I did not understand this exactly, but the idea made intuitive sense to me. Yeah, anything to add from anyone? I think we have reached the end.
I think G is in some ways the learned matrix, right? The weights, learned weights during the training.
Yeah, so in this case, G is like a decoder, right? So we encode X using F function, and then we select in some way
I see.
Z,
Okay. Yeah.
and then we decode, and that's G, decoder.
Yeah. Makes sense.
Yeah, I think it's kind of this example is in some way, I don't know, maybe more confusing than it is like it's kind of as so simple that it feels too abstract, right? It's, I don't know, like,
yeah, the thing in particular, as I said, in the context of the probabilistic explanations, the thing in the diagram that somewhat confuses me is, at least in this example, how he, for lack of a better word, the Z is separated from the X, whereas in a probabilistic situation, as the explanation unfolds in that other lecture, the point is that from X, you get to Z's, and your neural network is actually helping, which is the encoder. It helps you to map the X to Z. If you assume, for example, that Z is a Gaussian, then the axis, the network helps to map the axis to for a Gaussian, gives you the mu and the sigma, and you sample then from the mu and the sigma, or you introduce a little bit of noise, and then you get through the decoder to get the same axis if you think of it in an auto-encoding model. But that's where I get lost with this example a little bit. A lot of it makes sense, but where I miss out, and I need to dive into his lecture to see what I'm missing, is this here, the predictor from X and the Z kind of comes independently into the decoder. That's the part that.
So here, because we have a very simple problem, we just take a predefined range of Z's, and then we evaluate energy function for all those Z's, and then we, depending on our choice of temperature, either take the minimum or the soft minimum, right, of an energy function for over all that range of Z's. But in any practical case, you probably cannot like densely sample all the possible range of these that make sense for a problem. Right? We don't even know what that range would be in most cases, and that is why I'm saying that this particular example kind of feels too like detached from reality, or I don't know. So, and that is why probably we want to overcome that. So we don't want to do this explicit evaluation and minimization over z for the energy function, because it's not computationally efficient or probably even possible.
Feasible
Right?
for high dimensional Z's, for example.
Yeah, and even worse, we don't know if our selection of z is like good or not.
Appropriate.
Yeah, so there are like in real world problems, I think there are too many unknowns to map this setting directly to that, and like this variational autoencoders and stuff are probably like one way to like circumvent this problem, right? So we instead of selecting, so there we also select some kind of z a priori, which is our prior distribution, right? And we can set it to some simple distribution like a Gaussian, and then we can just sample from a Gaussian, but we also so that would probably that would put too much like in that case we have kind of like an unconditional decoder, right? If we just sample from the Gaussian, and we don't have this predictor and don't have any dependency of z z like over x, then our decoder would just map the data distribution directly, right? So we just and the z will be used could be used just to, I don't know, to make it to evaluate to particular, like it would be like a seed, just a seed which does not carry any particular information. But by making z dependent on the output of inference model, right? We make it that our training in this autoencoding fashion makes sense. So our z encodes some information about x, and the decoder should output the same x, right?
Yeah, that makes sense. Yeah, so I think that what you said makes sense now with respect to the diagram. Basically, this is, you can think of, or at least I can think of it as, this diagram kind of explains the, simple case of trying to do it explicitly when Z can be simplified to like a y1, y2, 2-dimension. So you can do it explicitly. Or he could have taken the example of a mixture of Gaussians, that kind of stuff. So in this case, he even simplified it to not even be that complex, but just be 2-dimensional y1, y2.
Yeah, it's actually even simpler. It's just a simple line, 0 to 2 pi.
Yeah.
Right. So, yeah.
Yeah, z is varying from 0 to 2 pi, and we know exactly what to do with that z. We just multiply it with this f of x, because we know that that will give us the ellipse, and we already knew that that's what we want. But in a general case, it's part of a function, since we don't know exactly how this latent variable interacts with the x. So that's why it's in a function. And here we just multiply it, I think. Sorry. Yeah, here we just multiply it with the x. Yeah. Okay. Any other points to add? Okay, if not, I think we can call it a day. This might be the last lecture of the course. So thanks everyone for staying with, staying with the meetups. I think we started in like January or something. So thanks to all of you who contributed and made this lively. I think it was really useful for me, and hopefully it was useful for you guys as well. Yep. Thank you.
Yeah, thanks for doing it, Gautam. I think a lot of very useful concepts, and appreciate you sticking with it and taking us through entire course.
Yes,
Thanks, everyone.
thanks for starting it. It was an interesting course. Although, like, its name is a bit kind of like deceptive. I think it's
that's true.
It was called practical, and it turned out to be like a lot of theoretical concepts which we are still struggling to relate to practice. Right? That's funny.
Yeah.
Yeah, I basically joined to learn PyTorch, but obviously it's much more than that.
Yeah, I learned a lot of new things and learned many things that I did not know existed. At least I know what I don't know now, so I know what to learn. Yeah. Okay. Yep. So I'll let you guys know if we'll be doing the other 2 lectures as well. Otherwise, yeah, we'll just end it here. Thanks, everyone.
Thanks, Gautam.
Bye bye.
Thanks, guys. Bye.